Now, before we dive into our next theorem, we want to define a couple of terms. A sequence AN is increasing if AN is less than or equal to AN plus 1 for all n in the natural numbers. So if you go one higher in the index, the number is going to be at least as high, the value will be at least as big as the original index. Decreasing, the sequence is decreasing if AN is greater than or equal to AN plus 1 for all n in the natural numbers. And finally, it's monotone if it's either one of those, increasing or decreasing. Now, this takes a minute to talk about. I don't particularly like either of the first two terms. A better term for increasing, well, by this definition of increasing and decreasing, this sequence is both increasing and decreasing. It's the constant sequence. That's because the equals here and the equals there. What's the term? What would be a better term than increasing for this? Non-decreasing. This one, a better term would be non-increasing. And I'm going to try to use those. If, in fact, the equal signs are not there, if it's a strict less than and a strict greater than, I usually call it strictly increasing, strictly decreasing. You'll never find two in a row that have the same value. But the textbook likes this. We'll just make sure it's clear whenever we use these terms. All right, well, theorem 1.16 states the following. A monotone sequence is convergent if and only if it's bounded. I was going to stop and let you guys try to guess what that word was. A monotone sequence is convergent if and only if it's bounded. We're going to write down this proof, and the whole proof is just 6 or 7 lines, and it's going in two directions. Remember, this if and only if is like that biconditional. This implies that, and the right-hand side implies the left-hand side. I usually do the left to right first, but since actually, in this case, I am going to do that. It is the easy one. Let's do the left implies the right. A monotone sequence, so if we, I don't even need to create a sentence in this case. I'm just going to say convergence implies bounded. And that's by theorem 1.12. That was an easy case to prove. Every convergent sequence is bounded. So we've got half of the proof already done. Now the other half is going to take about 5 lines, but that's all right. All right, well, so now we have to start off with, let's see. It's a monotone, so we need to assume, I'm going to assume one way or the other. I'm going to assume that it's an increasing sequence. Assume AN is an increasing sequence. We're starting with a monotone sequence. Now, what I normally write in parentheses here is, well, suppose it's decreasing. The proof is going to be almost identical except for a couple of characters. So I frequently will say that if it's decreasing, the proof is similar, and that's acceptable because it is, like I said, nearly identical. So we'll assume that it's an increasing sequence. since this set, and I'm writing it this way, this represents all the elements of the sequence. I'm writing it kind of in the set format because it's a set that has an upper bound. If this set of elements, AN, since it has an upper bound, I'll abbreviate that by UB. What do we know about a set that has an upper bound? That means it has a least upper bound, or the supremum. So we're going to let S be the supremum of that set. And conveniently, we will show that AN converges to S. That's what we're trying to do now, is prove that the sequence is convergent. Well, anytime we want to show that a particular sequence converges to a particular number, we started off by saying let epsilon be given. Let epsilon greater than 0 be given, and we're going to have to find a capital N. Well, let's let capital N be such that this A subscript N is in between S minus epsilon and S. Notice it's strictly, AN is strictly greater than S minus epsilon, and it's less than or equal to S. Anybody remember why I'm allowed to say that? I just said, let it be such that. Why am I allowed to make that statement? Anybody remember? Well, what is S? It's the supremum of a set. So, let me just draw a little picture here. I'll erase this in a minute. Let's say that's S. If that's the supremum of a set S, and this is the elements, I'm just going to mark them as X's. This is the elements of the set. It's going to get closer and closer to that S. S might actually be even in this set. But if there weren't if there were no element in this area right here that I'm highlighting, if there were no such element, then S would not be the greatest, the least upper bound. It would not be the supremum. I could say, oh, well, S minus epsilon is an upper bound that's lower. So because of our definition of S, this absolutely has to exist. So if you wanted to say this is possible, we know N exists because S is the supremum of that set. Thus, N, little n greater than that capital N, implies that S minus epsilon less than AN, that's a capital N, less than or equal to A lowercase n, less than or equal to S, less than or equal to S plus epsilon. That inequality has to hold. Well, this part of it comes from this inequality right here. Well, since n, little n, is at least as big as capital N, this has to hold, because we have a monotone sequence, and specifically for this, an increasing sequence, non-decreasing sequence. Every element in the set is less than or equal to S, and I just tack this on for the fun of it, less than S plus epsilon, because why? All that means is that AN minus S in absolute values is less than epsilon. That's equivalent. So we took an arbitrary epsilon and we found the capital N that makes this statement true. And just by the definition, therefore, AN converges to S. We obtained that S as being the supremum of the set, and it turns out that the sequence converges to that set, or to that value. So essentially we have something like this. We have an increasing sequence. I'm drawing it like a function. Increasing, but it may never hit S. It's possible it could. At some point forward, every element of it could be equal to S, but that's not, well, we don't know that. So for every epsilon, if this were S minus epsilon here, we've got all of these terms in between S and S minus epsilon, which of course means they're between S plus epsilon and S minus epsilon as well. We only did that because that's what was required for the by the definition of the limit of the sequence. Any questions on either the definition, the statement of the theorem, or the proof?